Exam solutions to your thermochemistry test. Questions are in random order. We have a glass filled with water and ice. Glass filled with water and there's ice cubes in there, and that's left at room temperature. Describe the direction of heat flow. Heat flows from the object with higher temperature to the object with lower temperature. That's a lot of arrows. In this case, if it's within the glass, the water liquid portion has a higher temperature than the ice cubes. So you could say heat flows from the liquid to the ice cube. So the system in this case would be the ice cubes, ice, and the surroundings would be the liquid water. This is an endothermic process because the system is gaining energy. The system, being the ice, is gaining energy from the surroundings, liquid water. Now, if you said the room was the surroundings, then it would be the same answer. It would be endothermic. In this case, the glass is the system. The cup of water is the system, and then the surroundings is the room. In either case, it's endothermic. The system is gaining energy. You should have specified the system and the surrounding to make your answer clear. We are adding some amount of energy to some mass of an unknown substance, and we note a change in temperature. What is this unknown substance? We're given this reference sheet, so we're going to use Q is equal to mc delta T, and we're given everything but specific heat. So let's rearrange this to solve for specific heat. Divide through by mass and change in temperature, and you get Q over m delta T. You just plug these numbers in. The amount of energy is given is 198 joules. And then the mass we're given is 10.0 grams. And then the change in temperature, it says, is raised by, so that's going to be 22 minus, the difference is positive 22 degrees Celsius. Let's take out our calculators. 198 divided by 10 divided by 22. And the specific heat of this unknown substance is 0.9 joules per gram degrees Celsius. So let's look at our table here. That would be, we're using joules here, so we use this column right here, and it's going to be aluminum. Aluminum is the answer, or Al. Calculate the heat flow in calories. So again, heat flow is Q is equal to mc delta T. We know the specific heat of water is 1 calorie. That's how the calorie is defined. 1 calorie is the amount of energy needed to raise 1 gram of water by 1 degree Celsius. That's how we define specific heat of water. Okay, so calculate the heat. It's already set up the way we need it. The mass given is 32.1 grams. The specific heat is 1 calories. And then the change in temperature is final minus initial. So it's got to be 40 minus 50. So you're going to get a negative number here. Let's punch these numbers in. Let's cancel out these Celsius. Grams cancel out. We'll be left with energy in terms of calories. All right, 40 minus 50 is negative 10. So negative 10 times 32.1 divided by nothing. So that's actually negative 321 calories. Next one. All right, calculate the internal energy. All right, so we know the internal energy of the system is equal to heat plus work. So what does it tell us? It's an exothermic process, so it's losing heat, and 1.4 kilojoules is done on the system. So let's just plug these numbers in. Q is going to be negative 10.2 kilojoules, and then work done is 1.4 kilojoules. All right, so let's add these numbers up. Negative 10.2 plus 1.4 is negative 8.8. kilojoules is the change in internal energy. That was given on your formula sheet also. So that was on your formula sheet. What quantity of heat is required to, this was very similar to your practice problem set. I think all of these were actually. The quantity of heat required to raise, all right, so we're given mass. We're given some information here about substance X. We're given change in temperature. All right, so looks like this is going to go between a phase change, so -20 to 10. We're going to have to cross the melting point. So it might help to draw the phase diagram for this one. So let's do that. I'm sorry, the heating curve. All right, so we got it's kind of like a generic heating curve like that. And we are starting, where are we starting? Negative. So here, let's label these points. All right, there's the melting point of -15. That's all we need to know. Let's label the boiling point as well. It's given to us. So it always helps just visualizing what the problem is asking you to do. So it's asking you to start from -20 degrees, which is below the melting point. It's telling you start there and end up there. All right, so -20 is below, right, is below this phase change, below that melting point. So we'll say we'll start right there. And so we need to take it to that melting point. So when you have a slope here, oh man, I'm going to need more room. All right, I'm going to draw, guess I'll do this, I'll write small. All right, so Q is equal to MC delta T. And so the mass here, it was given to us was 25 grams. 25 grams. And then the specific heat of the stuff at the solid form, there's a specific heat of the solid form, is 3 joules per grams degrees Celsius. All right, I'm not writing all my digits now. I'll do sig figs at the end. And then the change in temperature is from negative, so this right here is -20. To get to -15 is the melting point. That's a 5-degree increase. The change in temperature is 5 degrees. So let's punch those numbers in. All right, cancel out my Celsius, cancel out my grams. Okay, 25 times 3 times 5. 375 joules is how much energy it takes to get from this starting point. Just follow that green line. Now I'm going to pick a different color here. I'll use orange. This is going to, now we need the energy to melt this stuff, 25 grams of this stuff. So this right here in orange, I'll do right here. So I'll separate. So that's a phase change. So there's no change in temperature. When you go from solid to liquid, that's called fusion. It's called melting, but we're going to use the heat of fusion or the enthalpy of fusion for that. All right, so that is going to that's going to be in moles. So we're going to have to convert this grams into moles. All right, so we're given 25 grams of substance X, and the molar mass is given to us. Molar mass is 100 grams per mole. So we need to get moles because the heat of fusion is in moles. Now, if it was in grams, we wouldn't have to do this. All right, so 100 grams per mole. All right, so grams of X cancels out, and now we're left with moles. So now that we have moles, we can, oh man, there's too many X's here. All right, we're going to multiply that by this heat of fusion, where we put moles of the substance X. For 1 mole to melt, it needs 5.0 kilojoules of energy. All right, so let's punch those numbers in. 25 divided by 100 times 5, 1.25 kilojoules. All right, so that took us across that melting point, and now we need to get to, what did the problem say? Get it up to 10 degrees Celsius. So let's pick a different color. Do purple. All right, so we're going to try to take it 10 degrees. We're at negative 15, so we got to get it somewhere like there-ish. All right, let's say that's 10. All right, so that's a liquid now, so we're going to need the specific heat of the liquid portion, Q equals MC delta T. All right, so the mass hasn't changed this whole time. It's 25 grams. Now the specific heat we'll have to use is the liquid is 2.5 joules per gram degree Celsius. And then the change in temperature is 10 minus, final minus initial, negative 15. 10 minus negative 15 is 25 degrees Celsius change. All right, we can cross out the Celsius, cross out the grams. Should have left myself a little more room for this problem. 25 times 2.5 times 25 again. All right, so we get 1,562.5 joules. Now we got to add all of these numbers up. Now the problem with that is we're in joules here, and we're in joules here, and we're in kilojoules here. So this can't add apples and oranges. We've got to, the easiest thing to do is convert these joules into kilojoules. So we can move the decimal over 3 times, 1, 2, 3, change that comma to a decimal, and we get 1.56 kilojoules for that. And then over here, move the decimal 3 times, 1, 2, 3, and then you can turn that into kilojoules, so it's 0.375 kilojoules over there. All right, kind of running all over the place here. And then our final answer, just add them all up. 1.56 plus 1.25 plus 0.3, oh, sorry, this number, 0.375, and how many sig figs? That's three sig figs. 3.19 kilojoules is what we need. Sorry, this number has 2 sig figs, and so 3.19 is good. 3.2 is also good. We'll accept both of them. And if you got to, if you just got to the end and or close to the end and didn't convert these to kilojoules, then I believe you got half credit. I don't know exactly what number that is, but if you got that far, it automatically gave you half credit. Moving on. What is the change in enthalpy? Well, there it is. That's the change in enthalpy when 1.2 moles of carbon dioxide. So let's start with what's given. 1.25 moles of carbon dioxide. Did I say carbon monoxide? Sorry, carbon dioxide is what I meant. And how much, what's the change in enthalpy? So where's carbon dioxide? For every 4 moles of carbon dioxide, this is going to use up 2,599 kilojoules of energy. So the moles has to go on the bottom to cancel out the moles that we already have. And then that's going to require 2,599 kilojoules. Moles cancel out. Punch, punch. 1.25 times 2,599. How many significant figures? We need 3 significant figures here. Okay. Use scientific notation. 3 point, what did I say? 3 sig figs. 3.25 times 10 to the 3 kilojoules. Well, this is it's an endothermic process because delta H is positive. Just make sure I did my math here. No, I didn't do that right. Hold on. Go back. I forgot to divide by 4. I think. All right, so 1.25 times 2,599 divided by 4. Yikes, that's a different number. All right, sorry about that. So the answer is 812. kilojoules. Yeah, no need for scientific notation. All right, and it's positive again. All right, that's endothermic. And then next problem here, where's my, is the same reaction just flipped. So if the previous one was endothermic, this is exothermic. We just flip the arrows. All right, so this is we're given grams this time. So this time we'll need the molar mass off the periodic table, which you were provided. So let's start with the mass, 8.80 grams of C2H2, and then convert that to moles. All right, so carbon has a molar mass of 12. Let's go with more precision than that. 12.01 times 2, that's 24.02 grams per mole. And then the hydrogen, 1.01 times 2, 2.02. Add them up, and you're going to get 26.04 grams per mole. Grams cancel out. And now we can how many moles? 2 moles. For every 2 moles, it's going to produce 2599 kilojoules of energy. All right, cancel. 8.8. 8.8 divided by 26.04 times negative 2599. Oh, divided by 2. Oh man, I almost forgot that again. So it's going to be negative 439 kilojoules. All right, if we make sure how many sig figs? 3 sig figs, yeah. So if we start with 8.8 grams of C2H2 acetylene, which we use to blow up our never mind. Let's just keep going. So there it is. I think it was our flask or Gatorade bottle in one of our labs. How much heat is required to convert 12.5 grams of water, boiling point. So this is just a phase change. We don't need to draw a heating curve. All right, so let's start with 12.5 grams of water. Now, this is the heat of fusion and heat of vaporization table we gave you on your reference sheet. Water has a molar heat of vaporization, right, of 40.7 kilojoules is how much energy is required to turn liquid water to steam. 1 mole of it requires 40.7 kilojoules. All right, but that's in moles, so we need to convert grams to moles, right, for water. All right, so molar mass of water is 1.01 times 2 is 2.02, and then oxygen is 16.00. You add them up, 18.02 grams per mole. That's right off your periodic table, is the molar mass of water. All right, cancel, and then now we can use this molar heat of vaporization. So for 1 mole of water, it's going to require 40.7 kilojoules of energy. But we don't have 1 mole, we have 12.5 grams. It's going to be a little less than 1 mole. Sorry, 12.5 divided by 18.02 times 40.7. So the answer is going to be 28.2 kilojoules of energy or heat is required. All right, 3 significant figures. Yep. Moving on. 21 minutes, okay. So the following reaction occurs under constant pressure. So we are given Delta H is equal to heat when the pressure is constant. So when this is the thermochemical equation, we write the heat as a reactant or a product. Now, if it's written as a product, this is releasing heat, so that's exothermic. So exothermic means we just switch the sign to negative. It is losing. All right, so delta H is, get the unit back on there, negative 72.3. So all you have to do is just write that as with a negative sign. This is right out of your review worksheet. The law of conservation of energy states that energy is created. Oh, I hope nobody got that one wrong. It's like the opposite of what that says. If you add the same amount of heat to an equal mass of steam, mercury, and iron solid, if you had the same amount of heat, which one would end up having the highest temperature? Ugh. Okay, I need that chart again. Steam, mercury, and iron. Steam, iron, and what? Steam, mercury, and iron. Steam, mercury, and iron. Steam, mercury, and iron. Ah, here it is. So you were given this thing. Steam. Oh, here it is. Pick a color. There we go. Steam has a specific heat of 1.9. Mercury is the lowest one. So mercury is going to have the biggest temperature change. And what was the other one? Iron. All right, so mercury is going to have the biggest temperature change because it has the lowest specific heat. So the specific heat says amount of energy, amount of heat required to change the temperature of 1 gram of that substance by 1 degree Celsius. So if you add the same amount of heat to all of these things, mercury is going to change the highest temperature is going to be mercury. All right, we are given the potential energy diagrams. We did this in class, something very similar. So select these statements that are true. Let's check out what these statements are saying. A is endothermic. Endothermic, it is means it's absorbing energy. So B is this is endothermic. All right, so the reactants are absorbing energy, and therefore the products will end up with more energy. So this is endothermic, and this is exothermic. So A is exothermic, B is endothermic. That one is true. What else? Oh, well, these violate the conservation law, so that's neither of them are true. Answer is the second choice on my screen, but your choices are all shuffled around. Select. So we had the same heating curve in class. I gave you the same diagram. This is the heating curve of water, and I pointed out two things in class because I knew they were going to be on your test. One is let's see, the heat of fusion is greater than the heat of vaporization. Well, that is definitely true. The heat of fusion is the energy required to go, all right, so here's your solid, here's your liquid, here's your gas. So to go from liquid to gas, you've got to cross this heat of fusion. So this is the heat, or delta H, of fusion. It is definitely requires more energy, than the heat of, oh, I'm sorry. Sorry, this is heat of vaporization. I was just reading the problem. This is the heat of fusion. All right, so it is, so hold on, let me read that statement again. The heat of vaporization, yeah, so this is true. The heat of vaporization is greater than the heat of fusion, for sure, for water. It takes a lot more energy to boil a sample of water than that same sample of water for it to melt. All right, so this area is much, this is not even maybe drawn the scale, probably. So it should be even more than that. Remember, it was like 40. This was like 40.7 kilojoules per mole from our other problem. And then the heat of fusion is like 6, I think. So this here. Oh, so this one's not true. The first statement is not true. All right, the third statement, the solid form has a higher specific heat than the liquid form. The liquid, the solid form has the highest specific. The liquid form has the highest specific heat because you can see the slope. Right, the slope here is the least heat. I'm kind of exaggerating in it. Right, it goes vertical more. I'm sorry, horizontal more. Oh man, I'm sorry. So it goes across the x-axis more than the solid or the gas. And you even had that reference sheet if you wanted to. You can go back here and you don't even need that heating curve. You know water, liquid water has the highest specific heat versus ice or steam. So you could have gotten that answer either using that reference or just interpreting this heating curve, which again we did this in class. So there it is. Oh, gaseous was also a choice, but the liquid has the highest. So those are your two choices for that one. All right, are we almost done? Looks like we're almost done. So this is a phase change diagram. Uh, Phase changes are occurring. Well, B and D, those are your phase changes. Those are when you add energy, which is going around the x-axis, the temperature does not change. So it's B and D. It's called melting point or freezing point there, and the vaporization and condensation. I'll add point D. One more to go, last one. So this one was 1 point each. Can't fit this all on one screen, so these were just your vocab types of questions. So this is the definition of specific heat. This is the study of heat measurements is called calorimetry. And when delta H is negative, that is exothermic. And under constant pressure, what's the rest of that say? Oh, the heat content of a substance, that's enthalpy. Is that what's up here? Yes. So enthalpy is equal to heat under constant pressure. That was on your formula sheet too. All right.